Today we will learn how to convert a particular given NFA to DFA. So far we have learned what a NFA is and what a DFA is. So let us revise in brief what is the basic difference between NFA and DFA. Both are the part of finite automaton. In case of DFA, one state can transit from another state for a particular input, means it will move to a particular state only, that is fixed. It cannot move to more than one states. But this is not the case in NFA. In case of NFA, for particular input, one state can move to zero number of states, it can move to one state, it can move to more than one states. Now what is our job? Our job will be, we will be given a machine named say M. It can be anything, but here we are depicting the machine as M. Obviously it is a 5-tuple machine and it will be an NFA, and we have to find an equivalent machine in the sense whatever the language this NFA can generate, the DFA should generate the same language, right? We have learned what language is, what the string is, so we have to generate an equivalent DFA. It will be 5-tuple machine obviously, and the generation of language should be equivalent. Now we will see how to proceed. So this is the algorithm of converting a particular NFA to a DFA. So it will be much more clearer when we will visit some examples. For now, let us see what the algorithm says. Here our input will be a NFA or an NDFA. NDFA or NFA, the meaning is same, non-deterministic finite automaton, and output will be an equivalent DFA of it. First, what we have to do, create state table from the given NDFA. The case may be like this: you are given with a state diagram or a transition diagram. You have to create one state table or state transition table. If transition table or state table is already given, so no need to do this, perform this step, right? We can directly move to step 2. Here step 2 says create a blank state table under possible input alphabets for the equivalent DFA. It will be clearer when we will see the example. We will create a blank state table and where there will be possible inputs of the alphabets, or the possible inputs that will be specified under the sigma. So we can create blank table using the sigma. Next, step 3 says mark the state table of the DFA by Q0, means here the start state will be same as that of in DFA. Whatever the start state was there in NFA, it will be similarly copied in DFA. Now find out the combination of the states, all the states Q0 to Qn for each possible input alphabet. As we know that in NFA, say for state Q0 we have given one input 0, so there is a possibility that it can move to other state, it can stay at Q0 only, it can move to more than one states, right? So we have to write all the combinations there where it is moving for a particular input. Next, each time we generate a new DFA state under the input alphabet column, we have to reiterate the step number 4, right? Then the states which contain any of the final states of the NDFA are the final states of the DFA. Let us see with an example, it will be clearer. Fine, so this is the question given. What it is doing, there are 3 states, Q0 is the initial state and Q2 is the final state. For 0th input at Q0, it is generating Q0 only, or it is remaining in the Q0 only. For 1, it is moving to Q1, but if you see at Q1, if I put 0, it can either stay at Q1 itself or may move to Q2, or it will stay at Q1, and for 0 at Q2 it will stay there only, but for 1 it can either come back to Q1 or may stay at Q2. So let us develop the transition table now. See, as we have seen, there were 3 states, so we have put it, we have marked 2 input symbols 0 and 1 and have marked that Q0 as the initial state and Q2 as the final state. There are 2 notations which we use to depict a final state in the state transition table. Either you may mark it with a star or you may put a single circle, right? So for 0 we have already seen that q0 will remain at q0 only. For 1 it will transit to q1, and for the case of q1 it can either move to q1 or q2 for 0th input, and for 1 it will remain in q1 only, and similarly for q2. Now what is our final state, what was our final state rather in NFA? Q2, right? So whenever we will draw the diagram, we have to see where q2 is lying, right? Now here what we have to do, we have to generate the new steps, right? Because here the new states are getting generated, since in NFA for a particular input it can move to only one input, so we have to see what are the new states generating. So from the transition table we have seen for 0 input at q0 it will be at q0, for 1 it will be moved to q1, but for q1 if we give 0, the state generated is q1 comma q2. So please notice here that q1 comma q2 is our new state, we depicted as a new state, and obviously since q2 is there, this will be one of the final states. Similarly, when I put 1 at q1, it will be q at q1 only, and you can see the similarly for q2. For putting 0 at q2, it will remain at q2. For 1, it will generate a new state called q1 q2, but we are not marking it as new because we have already marked it as new in the previous transitions. Now our newly generated state is q1 q2, so we have to find out what it is doing if we supply 0 to it and what it is doing if we supply 1 to it, because only the input symbols available are 0 and 1, no more input symbols are available. Now to show the transition, what we will do, we will just make the union of these two newly states available. So transition of q1 q2 for 0 will be same as if we put 0 to q1 what it gives, and if we put 0 to q2 what it gives, and the union of 2. As you can consult the table or the diagram, you will come to know that it will generate q1 q2 only. Similarly, if we put q1, it will generate q1 q2 only. But now see, it is not generating any more new states because we have already marked q1 q2 as a new state. So let us see what the DFA will result in. So what are our states now? q0, q1, q2 and q1 comma q2. So you can easily understand that there will be two final states, one containing q2, another containing q1 comma q2, right? So these are the transitions. We have already find it out in our previous slides, and this will be the transition diagram. So it is, you can easily convert it, the table to the diagram. We have already learned it, right? So what we are doing, the state q2 can be eliminated because q2 is an unreachable state. So here q is of no meaning, right? We can never reach q2 from any one of the states. So sometimes you can eliminate this, as we have seen in the examples of the DFA, some transitions where we have omitted intentionally, and I have already told you to mark those transition putting a date state or a state which is unreachable. So this is an example. You can see, you can mark like this. Fine, let us see one more example. This is the NFA given. So how many states are there? There are 5 states. What are the initial and final state? A is initial state and E is the final state. So let us make the transition table. You can easily make it, I think so. Here in a new fashion I have developed this table. We have, instead of writing input equals to 0 and 1, I have written the transition function, that is delta of q0 comma 1 and delta of q comma 1. Means for 0 where it is moving, for 1 where it is moving. So you can easily consult the diagram and can make this table. So if we have to convert to DFA, I have not shown the steps again, you can try it at your own. So what it is doing, for A, if we give it 0, it will generate a state A, B, C, D, E, and for 1 it will generate D, E. So what are the new states generating? Both of them are new states. It is not, it should be treated as an individual state in case of DFA. So we will find out what A, B, C, D, E is doing for 0 and 1. You know, we have to find out the union of all. We have to find out what A does when it is given 0, what B does when it is given 0, what C does, what D does, and what E does, and we have to make the union of all. Similarly for DE. So in this fashion, if you proceed, you can generate this table. Just take your time and use a pen and paper, and you can follow the steps as explained in the previous slide, and can try this out. Now the corresponding diagram, it is very easy. If we can make the transition table, we can make the transition diagram very easily. One thing we have to keep in mind, in our NFA, what was our final state? It was E, right? So wherever E is present, we have to mark every state as the final state. So this the thing you have to keep in your mind. So here you can see, for at any one of the state, for a particular input, it is generating only one state, right? So it is a DFA. Fine. Next we will see another very important part of our syllabus, that is how to convert an NFA with epsilon moves to DFA. We have seen what in an NFA is with epsilon moves. Epsilon means null moves. So we our job may be to remove those null moves, because to generate DFA we have to be stricter enough, right? So what NFA with epsilon move does, if any finite automata contains epsilon transition or move, the finite automata is called NFA with epsilon move. So here a new concept will come. We have to find out epsilon closure. I am just reading out what epsilon closure says. As we visit the example, the concept will be clear, right? So epsilon closure for a given state A means a set of states which can be reached from state A only with epsilon moves, including the state A itself. So for each and every state we have to find the epsilon closure of it. Let us see an example, it will be clearer. Fine. So here first we will see the steps which we will follow for converting an NFA with epsilon moves to DFA. Step 1 says we will take the epsilon closure for the starting state of NFA as a starting state of DFA. Then find the states for each input symbol that can be traversed from the present. That means the union of transition value and their closures for each state of NFA present in the current state of DFA. This will be clearer when we see an example. Fine. Then step 3, if we found a new state, take it as current state and repeat step 2. Means by repeating step 2, how to do that we will see in the next slide, and we will keep on finding out the epsilon closures of the states. Step 4, repeat step 2 and 3 until there is no new state present in the transition table of DFA. And step 5, mark the states of DFA as the final state which contains the final state of NFA. Fine. Now let us see the example. Here an NFA with epsilon transition is given. So how to find out? Now as we have seen that epsilon closure means of a particular state that it will include the state itself and it is visiting with epsilon moves. If you consult the diagram, you will be able to see that Q0 is moving to Q1 and Q2 with epsilon moves. So the epsilon closure of Q0 will be Q0 itself, and it will include Q1 and Q2. But in case of Q1, Q2, Q3 and Q4, it is not moving to any other state with epsilon moves. So the epsilon closure of those states will be, that means itself only, right? For Q1 it will be Q1, for Q2 it will be Q2, and so on. Now what is the new state we have generated here? It is only Q0, Q1, Q2. Rest are already present in NFA. Now we are depicting this new state Q0, Q1, Q2 as state A for simplicity. You may keep it as Q0, Q1, Q2 only, no issue. Next, what we will do, as we know, since we have to draw the DFA, we need to know what state A, rather what state Q0, Q1, Q2 is doing for input 0 and what it is doing for input 1, since there are two input symbols available in this case. So here we are finding out the transition value. So epsilon, again we have to find out epsilon closure. What Q0, Q1 and Q2 is doing, we have to find out it for the transition of Q0 for 0, Q1 for 0 and Q2 for 0, and find out the union of all. Only extra feature is here, after finding out the these transitions, we have to find the epsilon closure of it. If you consult the previous slide, you can see that epsilon closure of Q3 is Q3. So let us say this is state B, right? And again for 1 at A, or rather Q0, Q1, Q2, we will find out similarly what the epsilon closure is. Again we are finding it out as Q3, and we have already marked it as B. So we can say this is the partial DFA. If you consult the previous slide, you can say that for A, if we give 0 at A, it will move to B. If we give 1 at A, it will move to B. That means Q0, Q1, Q2 is moving to Q3 for both input 0 and 1. So now this is not the end, we have to perform more. What we have to do next, we have to find out the closure for B, because we have marked the new state as B. So again B means what? Q3. So we have to find out a closure for Q3, epsilon closure for this transition function. So it is coming to 5, and again if you find it out for 1, it will be Q4. So new state we are marking it as C. Now again find out it for 0 and 1, you will get 5. So here no new states are generating. So now you can draw the diagram, and it will be like this. You can consult the previous slides, and the concept will be more clearer. Fine. And this is the end of our today's lecture. Next session we will learn how to minimize a given DFA so that the computational time can be reduced. Okay. Thank you.